Several phenomena contribute to the apparent motion of the Moon in the sky. Equally, as for the apparent motion of the Sun, the Earth's rotation determines the rising at the east and the setting at the west. The Earth inclination axis determines an angle on the horizon of all possible rising and setting points, whose amplitude depends on the latitude of the observer. The declinations of the maximal and minimal rising points are equal to the Earth inclination axis, that is, plus or minus 23 degrees at each side of east. Therefore, even for the Moon, we can define two lunar standstills, or lunistices, called northern and southern lunar standstills, to the north and to the south of east respectively. In the case of the Moon, we have other types of phenomena that contribute to its apparent motion, mainly the inclination of the lunar orbital plane and its precession. As we have seen, the lunar orbital plane is inclined of around 5 degrees with respect to the ecliptic. This adds around 5 degrees to the possible ranges of rising and setting points of the Moon, defining the major and minor lunar standstills. These 2 points are placed at plus and minus 5 degrees at each side of the solar standstills, that is, the solstices. We can therefore speak of major northern lunar standstill, minor northern lunar standstill, minor southern lunar standstill, and major southern lunar standstill. We can see that the arc of the major lunar standstills is always larger than the solar amplitude, and the arc of the minor lunar standstills is always smaller than the solar amplitude. The rising points of the Moon during the month change as a consequence of its revolution around the Earth, reaching a maximal and minimal point every month. The major lunar standstills, though, are the maximal possible rising points occurring with a cycle of about 18 years, with the latest major lunar standstill happening between 2024 and 2025. The periodicity is due to the precession of the line of the nodes, which rotates in time due to gravitational effects. The cycle of the lunistices overlaps on the cycle of the lunar phases in a complicated way. The lunistices can be reached during a full moon phase, but also during a new moon phase, or on the closed days. Considering that the full moon always rises opposite to the setting sun, we can say that, around the winter solstice, when the sun sets at the south of west, the full moon rises at the north of east. In the year of the lunistice, this full moon is the closest to the major northern lunar standstill. The full moon closest to the winter solstice is also the one that culminates higher in the sky and remains visible for the longest amount of time. To the contrary, around the summer solstice, the sun sets at the north of west, and the full moon rises at the south of east, closest to the major southern lunar standstill. The full moon closest to the summer solstice culminates lower in the sky and remains visible for the shortest amount of time. The periodicity of 18.6 years of the standstills is determined by the precession of the nodes of the lunar orbit. We have seen that the ecliptic and the lunar orbital plane intersect along a line that is called line of the nodes, and the intersections of this line with the lunar orbit are the nodes. When the gravitational pull acts on a rotating spherical body, such as the Moon or the Earth, it deforms it into an elongated shape. Then, the gravitational pull at the equator exerts a force that drives the body onto an orbit that rotates in time, around the rotational axis of the more massive body, in our case, the Earth. This movement is called precession, because the line of the nodes spins around, shifting forward, preceding. In particular, this type of precession is called nodal precession. It happens, therefore, that at the major lunar standstill, the lunar orbital plane is aligned opposite to the equatorial plane with respect to the ecliptic. so that its inclination adds up to the inclination of the Earth axis, for a total of around 28 degrees above the equatorial plane. About 9 years later, at half of a precessional cycle, the lunar orbit is aligned so that both the lunar orbit and the equatorial plane are at the same side of the ecliptic, achieving a minimum angle of around 18 degrees with respect to the equatorial plane, at the minor lunar standstill. Another consequence of the inclination of the lunar orbit are librations. In reality, we don't see just half of the lunar surface, but we can see up to 59% of its portion. The effect, visible only with some instrument, even of reduced zooming capabilities, implies that sometimes we see beyond each side of the lunar disk. We see beyond the eastern and the western border of the lunar disk thanks to the Earth's revolution, which sometimes chases and sometimes precedes the Moon along the orbit. We see beyond the north and the south poles, due to the Moon's inclination with respect to the Earth's equatorial plane, some of the lunar orbital inclination and its rotational axis, for a total of 6 degrees, offering us sometimes a view of its north pole and sometimes of its south pole. A third type of libration arises from the actual rotation of the Moon axis with respect to the vertical of its orbit, and its consequent axial precession, analogous to the more famous precession of the equinoxes on the Earth. The combined effect is an apparent wobbling of the Moon. A measure of the lunar libration is the location of the sub-Earth point, the blue one, and the sub-solar point, the yellow one. The points at which, from the lunar surface, the Earth and the Sun appear at the zenith respectively. When the sub-Earth point moves above or below the Moon's equator, we see more of the northern or southern region respectively. In an analogous way, when the sub-Earth point shifts towards the left or right side of the main meridian, we see more of the western or eastern limb respectively.